Routing is the first place where we go now deep into the internet itself. So we have seen so far how the network layer is organized, how we can use it with the transport layer, how we can have physical access with the MAC layer. And we have seen that in the network layer, we need those routing tables that can be aggregated and etc. But now the question is, how are they computed? So how do routers know how to get the tables? A bit of terminology. Routing is a word that is used with different meanings. This is very typical of computer science and even more of computer networking. The words need to be understood in a given context, and the paper and a SIGCOMM paper of today doesn't use the same words as a SIGCOMM paper of 25 years ago. So we need to be a bit careful. Routing can mean two things. It can mean packet forwarding by a router. So when a router forwards a packet, many people call that routing. So if you are a bridge, you bridge the packet or you switch the packet. So this is terminology that's often used. I will try not to use it. I will say packet forwarding instead, but that is very often used. So you have to be able to live with it. In this context here, routing means the computation of the routing tables. So the things that routers need to do to have the routing tables correct. Bridges do something similar, layer 2 switches. They do something similar. They have to build a spanning tree, and they have to learn the addresses by sniffing source addresses. So the equivalent of routing for bridges is spanning tree plus address sniffing. So address learning. Those are the equivalent of routing for layer 2. In routers, we don't do things at all in the same way. We don't force the distribution, the network to be a tree. We allow much more flexibility. So routing is not a real-time function. By real-time, I mean at the time scale of a packet. When a router receives a packet, its job is to get rid of it by forwarding it to the correct output as soon as possible. That's the real-time operation of a router. Routing doesn't have the same urgency. Routing is about modifying the tables when there's a change in the network. Of course, you want to do that as fast as possible, but routers are not able to do that at the same speed as they do packet forwarding. So if a link crashes somewhere in the internet, some routes need to be changed, so routers will need to change the data structure of their routing tables, but it may take to them up to several seconds to do it. So it's not a real-time function. The goal of a routing protocol is to find a route to every destination. So it needs in particular to learn what are the prefixes of interest in a given network. In a network like EPFL, we don't really need to learn because we use a default route. If I'm a router at EPFL, I need to learn what are the specific destinations inside EPFL. And for all the rest, I go to the default route. If I am a router that's a backbone at the backbone of the internet, then I don't have a default route. I need to learn all prefixes in the world, which for IPv4 is order of 500,000. So that's the size of the tables you need to learn. Typically, routers find a route by computing shortest paths. I'll say typically because things can be done differently, and in particular with software-defined networking like we use in the lab, you can modify the path as you want, but this is the most widespread technique. Routing protocols are, the first job goal of a routing protocol, if you design a routing protocol, the first thing you have to do is make sure it is plug and play. So if I take 20 routers, I configure them with the appropriate prefixes. I configure manually. I go with my bicycle to each of the places where the routers are. I have prepared on PowerPoint an addressing plan and a map of the network. I know which block of addresses in which interface. I go to every router. I program on each interface the correct blocks. And then I say start routing protocol. That's all I should have to do. So by starting the routing protocol on all of my 10 routers, they will discover all the routes. I don't need to manually go and to the routing table and route and go and write the values. And in particular, as soon if one of the router crashes, if I have enough redundancy in my network, the routing protocol should compute new routes that recover from the crash. That's the main goal. There are essentially 3 or 4, here I've listed 4 classes of methods for routing. There are more, in fact. In particular, you can imagine your own combination of all this, and you can do centralized applications that will manipulate that. But the centralized applications typically don't have this property of being plug and play. So if we talk of plug and play, here are the 3 or 4 typical ways. The first one is distance vector, and this is the one we will see today. With distance vector, it's the smartest intellectually. Every router knows only its neighbors and some local information on how to reach all possible distances. So the routers don't really know the global network, they just know who is around and which direction I should go. This is similar to what you do when you go somewhere with your car or bicycle and you don't have a GPS. You don't have a navigator. So what do? If you drive your car, and that was 30 years ago, you didn't have a GPS, and you have to go to Paris, how do you do? Well, if you're in France, you look for the Paris signs at intersections, which you find in every city, and you go in this direction. Right? This is how distance vector works. Link state is the GPS way. With link state, you have a map of the entire network, and every router knows the map of the entire network, and for every destination is able to compute where to go. Path vector is a variant of this that we will see when we use BGP. And source routing is, we will discuss after the break, I think I should. So we do a break and resume. Just mention source routing. Source routing is a very, very old routing method that was used in the 80s in the large corporate networks that were using token ring technologies. And it is used today in what is called ad hoc networking in emergency rescue operations. One of the protocols for ad hoc networking. Ad hoc networking is about when you have an earthquake or something bad that happens, then you come with portable routers, just laptops with truck batteries, and then you want to build a network that provides connectivity, and you don't have much time to design things. You don't go with your PowerPoint slides with everything. You just put them wherever you can put them and let the different routers discover each other and organize the network. And in the very extreme case, it can even be your portable device that is also participating in routing. One of such systems uses source routing, where source routing simply means that the route is computed by the source as opposed to computed by the intermediate system. So this is showing an example that was typical of the token ring times. The boxes would be token ring switches or ad hoc network switches. Then by some mechanism, when A has a packet to send to B, it needs to know a path to go to B. Here, a path is simply described as the collection of interfaces names like ETH0. There can be interface IP addresses. Here I'm using interface names or labels. For example, we see that the packet on the left sent by A has a route information which is 224. Well, it simply means A sends the packet to its default router. Then the default router does a stupid job. It goes to the routing information and reads the first element, which is 2, and sends it on this information. for example, sends it on interface number 2, which means the packet will reach here. If it's a point-to-point interface, it will reach the top router. Of course, it needs to mark the fact that it has consumed the label 2, so it needs to put a flag somewhere. When the second router receives it, it also sees a number 2, so it sends it to the third router that sees the number 4, and it sends it to B. So that is source routing. Source routing also exists in the internet in the form of a source routing header that can be added to IP packets, but it's practically not used. For security purposes, source routing headers in the standard internet, I would say, are not used. But in special cases, like ad hoc routing protocols, this can be used. So you see that the main virtue of this is that the router jobs is very easy. In fact, the routers are completely dumb. They don't even need to know anything about the topology. But this leaves aside the problem of how do the sources discover the routes. This is typically done by flooding mechanisms. So in a case like here, A would first need to send a broadcast packet to reach B. So a broadcast packet is a packet that would be sent to the first intermediate system that would then repeat it to the two neighbors. And while repeating this packet, these special packets are called explorer packets. These explorer packets accumulate the path that they are taking. So when A sends explorer packets to B, there are many routes in this network. For example, you can go via the top path or the bottom path or any combination of the two. And when that happens, all the different explorer packets, or at least the ones that are not dropped, will reach B, and within them, the packets, the routes that they have taken will be written. Of course, you could even have looping packets, but since the explorer packets contain the route that they have taken so far, one of the jobs of an intermediate system is, before repeating an explorer packet, before flooding it to all the ports other than the one on which it was received, it checks whether by sending it you would create a loop, or it checks whether a loop is already present, in which case you discard the packets that have loops. So this is typically how DSR, on-demand source routing for ad hoc networks or token ring source routing works. But the routing that we're interested in today is more distance vector routing. So what it does, distance vector routing computes a path to destination, and the path is by choice or by design the shortest path. Shortest according to some metric. The cost of a path, the metric of a path, is the sum of the cost of the links that constitute the path. And what is the cost of a link? Well, that depends on configuration. It could be the length in kilometers if you really want to do like Google Maps routing. But in the internet, it is probably more a cost that reflects the capability of the link. A low-speed link will have a high cost, and a high-speed link will have a small cost. If you have set up the cost, then you can compute the distances to all destinations. And the goal of distance vector routing is to compute all distances to all destinations. So it uses an algorithm that we will see in a minute, which is called distributed Bellman Ford. It is fully distributed, which was one of the requirements we had before. I have my network of 10 routers. I set them together. I connect them by Wi-Fi or by pulling wires. When they are connected, they discover each other and compute the paths in a fully distributed way. I don't need a centralized server like I have if I use software-defined networking. I don't have this here. We cannot have centralized server when we bootstrap a network. If you need a centralized server to connect to the network, you need to have a means of communication from the central server to all the nodes. So in many cases, we don't have that means, so we need a bootstrapping mechanism, which routing provides. A special feature of distance vector routing is that the only information it really uses is the distance from itself to all destinations. So it doesn't have a topology database like you would have if you use Google Maps with link state routing. It doesn't know where the routers are, what are the links, what are the costs. It knows its local configuration. It knows who are the neighbors, what is the cost of going to the neighbors. And for all destinations, what is the distance to that destination. And that's all that it knows. And this is a bit miraculous, and we'll see in detail how it does it. So let's start with a graph theoretical result. If you need to compute shortest paths on a graph, which algorithm do you use? You would use Dijkstra? Any other? So why would you use Dijkstra's algorithm? You said Dijkstra. Who said Dijkstra? You, sorry. Sorry. So why would you use Dijkstra's algorithm?
Because it works fine. It does the job.
Because it does the job, but is there a better one that does the job? No, Dijkstra is the optimal algorithm. We haven't found one with, well, at least in the general case, with better complexity. So Dijkstra is the best algorithm to compute shortest distances on graphs. Right? But there are other ones, like Bellman Ford. Here we use Bellman Ford, which has higher complexity than Dijkstra, but we will see that there are good reasons for using it here. The main reason is that Dijkstra cannot be distributed, cannot be made to run as by a message passing. It needs to be run centrally, whereas here Bellman Ford can be distributed. So this is one algorithm for computing shortest paths. As this discussion says, it's not the best one, but it's the one that's used for distance vector for good reasons. We will see in a second. And it's a very simple algorithm, like many graph theoretic things. It's simple once you see it. So the problem is to compute the distances from all nodes to one destination. So we call it destination one. So I have a graph, a directed graph with directed edges, a cost associated to every edge of the graph. And there is one particular node, one particular vertex, number one, to which we want to compute the destination, the cost of going there, the distance to that. So we put that in a vector. I call P the vector of the cost of going from node I to destination one. And the algorithm works as follows. First you say, so the superscript 0 means the initial value. Node 1 will say, I am at a distance 0 of myself. So this is a centralized version. So I am a central computer that knows the entire graph, and I can have access to everything. And then at iteration 0, I set the cost of going from I to 1 to infinite, because I know nothing initially. Then I will do a loop that will, at every step of the loop, will compute the minimum of Aij. Aij is the cost of the edge ij. So it's the cost of going from I to j, plus the cost in the previous iteration of going from j to 1. So if I want to go to 1, I look at all the j's. Of course, the only j's that I'm interested in are the ones that have a finite link cost. So if j is not a neighbor of I, Aij is infinite, so we don't need to look at it in this computation. So I go to all my neighbors, j. I compute what is the cost of going from me to this neighbor. What is the cost that this neighbor had computed of going from self to 1? I sum the two because the path costs are additive. And that gives me one possible value. If I go via j, I will have this value. I look at all my neighbors and I pick the best one. I take the minimum. This is why we have the minimum. And I consider that at round k, this is the best value I've had so far. If I do that for at every node. At 1, of course, I keep the distance of going to myself 0 because I know I want to go to 1 and I am at 1. And I do that until the algorithm becomes stationary. If it ever becomes stationary, if that never happens, the algorithm will loop forever. When it has reached the condition that the vector of cost I've computed is the same as in the previous round, I stop and I say, this is the cost of going there. This is the Bellman Ford algorithm. To understand why it works, first let's do a small simulation. I'm showing a graph here with 5 nodes called 1, B, C, D, E. So I call it 1 instead of A because it's 1 in the previous slide. And I'm showing on the left the round 0, so the initial value. The box is showing the value of the vector P. So initially I put a value of 0 to node 1, which is the destination. All the others, they don't know. They put a value infinity. Then when I do the first round, here is the values I will obtain. In the first round, what do I do? Well, if I am node B, for example, if I am node B, I look at all my neighbors, which are C, E, D, 1, so all other nodes, and I look at what it would cost for me to go towards 1 if I go via those neighbors, and if I accept the fact that the destination cost from this neighbor to 1 is what was obtained in the previous case. So if I am in B and I go via 1, I found the cost of 1 plus 0, which is 1. If I am in B and I go via C, I will find the cost of 6 plus infinity. So here we use the rules that a number plus infinity is equal to plus infinity. We will have plus infinity in this calculus, but never minus infinity. So there will never be problems of undetermination. So going via C is not a good idea. Similarly, going via E or via D is not a good idea. The best idea is to go directly via 1, and it gives me a cost of 1. The same at D, at node D. I find that I can go and I have a cost of 5. And C and E, they are less lucky. If they look at all their neighbors, they have an infinite cost. If you add the cost of going there, it still gives infinity. So this is what we will find at the end of iteration 1. Now iteration round 2. Before going to round 2, one interesting interpretation is to, what is that? Yes. Is that of message passing. We can imagine that this algorithm, which again is centralized so far, so we're not passing any message, but we can interpret it as if the nodes were talking to each other. So as if C was sending to E the information, my cost is infinite. And similarly, 1 is sending to E the information, my cost is 1, and etc. If we look at E, for example, when E does this computation, the job of E is to look around all the neighbors and see what they have. But we can interpret that as E receives from the neighbors messages about their costs. And this is what has been shown here. E has received the 3 costs, infinitely 1 and 5. It adds them to the cost of going to the neighbor from where the message comes. And that will give exactly the value predicted by the algorithm. Right. So an important way of thinking of this is that Bellman-Ford centralized can be interpreted as a synchronous message passing. In one round, synchronously, all nodes receive from all neighbors a message that contains the values at the previous round. And then a node computes the value for the next round. We will see that that's the core idea that's in distance vector routing. In distance vector, we'll do that exactly, except it will not be synchronous. The messages will go at their own pace here. So if we continue this, for example, this is what we will have for k equal 2. So at k equal 2, we find the values that are given here. So C believes it is at the distance of 7, which happens to be true in this case. E believes it is at the distance 3 of 1, etc. The theory or the algorithm hopes that it will stop because the stopping criterion is pk equal pk minus 1. will this stop? Or at least at which value will this algorithm stop here? I stop in 5 seconds. I close the poll in 5 seconds. And the correct answer is at k equals 4. We can continue the simulation. In fact, we can interpret very easily what Bellman Ford is computing in this example. If you look carefully at the first box, k equals 0, well, that's not so interesting. If you compute k equals 1, the values have a physical interpretation. What are they? The values that are in the boxes, the values computed by the algorithm at around k equals 1. How could you interpret them? Is the cost of going to 1 in 1 hop. Right? We see that node B and D, the cost of going to the destination in 1 hop is 1 of 5. C and E, the cost is infinite. They cannot go to 1 in 1 hop, right? In 1 or less, in 0 hop for 1. For k equals 2, it's the same. Is the cost of going to destination 1 in at most 2 hops. So if I'm allowed a budget of 2 hops, if I put packets with a TTL of 2, this is the best cost I can achieve at number 2. We see C, for example, is at the distance of 7 because the only 2-hop link, 2-hop path that goes to 1 is the path via B, CB1, and it has a cost of 7. At k equals 3, we find the cost of going there in up to 3 hops. Now, there is a path that is better. It's longer in number of hops, but it's shorter in terms of cost. That's the path that goes via E, from C via E. Here we see it has a total cost of 4, and etc. So it's fairly easy to show that by induction, that what Bellman Ford computes, at least with those initial conditions, is the cost of going from self, from a given node, to the destination in at most k hops. So in that case, we see that it terminates in k equals 4. That means at k equals 3, we had already computed the final value, which means all the best paths are at most 3 hops. Right. Now, this tells us why this algorithm works. If you have a finite graph that is connected, so if there is a path from anybody to 1, to destination 1, then there is the shortest path will be in a number of hops that is bounded by the depth of the graph. So in the worst case, the number of nodes minus 1. So there is a finite k such that the algorithm will stop. It will stop when it will have reached the diameter of the graph here. More precisely, the theorem says, the theorem of correctness of this algorithm says, if the network is fully connected, it stops. and outputs the in outmost k equal n. That means at n minus 1, it had, at worst case, it had found the correct destination. But this is a very, very coarse upper bound. Most networks are not, will stop much, much before. And when it stops, it outputs the correct destination, the correct cost. Because the cost of going there in at most n hops is the cost of going there, period. Number 2 is what I said before. We can interpret what happens at the end of round k. And number 3 is, in fact, something even more interesting. That says that once the algorithm has stopped, once I have found the value p, I can find the shortest path to the destination by analyzing this thing here. This thing here is, again, the message passing assumption. Assume the algorithm has converged. And all the neighbors tell you what is their cost of going to the destination. And then you compare all your neighbors. For each of your neighbors, the neighbor is P is J, you compare P of J, which is their cost of going there, plus the cost of me going to the neighbor. So that gives me one possible path and cost to go to the destination. Then the theory says, if I compare all of them, one of them must be the best path, because there is the shortest path from me to the destination. And the one that is the best path is the one that gives the minimum here. So in other words, by computing the minimum here, I find my value, which is fine. But more interestingly, for routing, it tells me how to go there. I should go through the neighbor that gives the smallest value in this computation here. Which means that by knowing only the vector p, by receiving from the neighbors their values of p, and knowing my value aij, of going from myself to my neighbors, I can compute the shortest path, which is the property of distance vector routing. All I know is messages received from the neighbors about their cost to destination, and from that, I can know how to go there. So for example, if we, here. If we are node C, and we apply this, when the algorithm has converged, here are the 5 values of P. If I am at node C, I can ask my neighbors B and E, what are their values? They are 1 and 3. Then I compute, I compare. If I go through B or through E, if I go through B, I find 7. If I go through E, I find 4. This is what we did at the last round before convergence. So all we need is to either remember the last thing we converged or compute it again. Then we will find that we need to go via E. So by simply receiving this information, C knows in order to reach 1, the shortest path is via E. So C has only local information from its neighbors. Voila, that's the first part of the theory. Now in practice, we don't run a centralized version of the algorithm. We will run it distributed. And when we run it distributed, we will also have to support cases where there are changes in the configuration. That's the primary goal of routing. Routing protocols have to adapt to changes. If they don't adapt, we don't need them. If you have a fixed configuration that never changes, then you can download in every node by some mechanism, with your bicycle or with a modem, whatever. You can download the configuration. If it's fixed and never changes, it's a bit cumbersome, but you will need it once forever. Of course, this is not what we have. Things can change. And changes can translate into the fact that the algorithm is running, and then something changes somewhere. For example, the cost of a link changes. What should we do? So one centralized view of the world would be, as soon as there is a change, you rerun the algorithm. But rerunning the algorithm means what? It means resetting all the nodes So press a reset button in all the Bellman Ford computations, in all routers in the world. That would be one way to do it. Not in the world, in the network in which we are applying this. But that's not very easy to do if the network has changed. So a change maybe, for example, a link is broken, so we're not sure we can reach all the nodes and tell them now restart the computation. So it may be difficult to implement such a thing. There are ways to do it, but they are clumsy. The assumption that is made here is that we would like to do without that. We would like to continue running the algorithm even if things have changed. Which seems a bit weird, but if it works, that would be nice. So does it work? That's the question now. Concretely, that would mean that I run the algorithm, but I start here not from the clean initial conditions, but I start from whatever state I was before the change. So I've been running Bellman Ford, perhaps it has converged, perhaps not. Then all of a sudden something changes. The cost of a link changes, for example, or a new node is added. And then I continue from there. It means we can abstract this by a more general situation where we run the algorithm from arbitrary initial conditions. The initial conditions are not anymore under our control. They are under our control if we can reset everybody. We can reset everyone and say, okay, put 0 to everyone, to your destination, to yourself, and plus infinity to everyone else. But if we don't do that, then we are in a case where we start from other initial conditions. What will happen? Close the poll in 5 seconds. So the majority says the algorithm converges, but not to the correct distances. Well, I will keep the suspense open. I will not answer the correct question. This is enforcing the differential encoding method. So whatever you think is right, you have to remember it, and then you will see what is the correct answer. To go towards the solution, let's go to a more specific thing here. So I run a simulation of this algorithm. And I ask you to do manually the simulation. I close in 5 seconds. I wait until the majority is right, and then I close. The correct answer is 2, so all we need is to do a simulation. We start from the panel on the left with those weird conditions. For example, B believes it is at the distance 10. Why does it believe it's at the distance 10? We don't really know. Perhaps there was a link before of cost 10 that went from B to 1. And CED believes they're at a distance of 1. Why do they believe that? We don't really know. But then we just run the algorithm. We can have the interpretation of message passing. So what does D2 do? D asks the neighbors, what are your values from the previous rounds? The values are 1 for E, 10 for B, and 0 for 1. So for E, it takes 1. 1 plus 1 gives 2. So if D chooses E, the value is 2. If D chooses B, the value will be 10 plus 2, which is 12, which is less good. I drop it. If D chooses 1, it gives 5 plus 1, which is 6. So the winning is 2. So because E believes in the previous round it is at the distance 1, D will believe in this round that it is at the distance of 2. So that's the value of 2 that will be here. And then I've done the simulation for all the different values, and we see what happens. We see that, for example, B, that was initially believing it's at a distance of 10, will ask all of its neighbors, what are your values? It will find 1 as one of the neighbors, so it will find a better than 10, which is 1. It will now forget about this 10 and give a value of 1. C, that was believing it is at a distance of 1, now ask all the neighbors, what are your values? And the best will be E, which is a value of 2. So C will increase. Now, the new value of C will be 2, not 1. Unlike what happens if we use the normal initial conditions, things can only decrease. Now they increase for some and decrease for others. And if we continue, we see that, at least in this case, we converge. We converge, it stops. At k equal 4, we have the same as at k equal 3. And does it converge to the correct values? Yes. The things to which it converges are exactly the correct values, in spite of this very strange initial conditions. Let's continue to evaluate. Assume now the problem is not so much that we had random initial values, but the incorrectness of the initial values are compounded by the fact that the network has become disconnected. So assume we break all the links along the red line here. There's an earthquake somewhere. All the lines that go west to east are broken. Right? Now, of course, when the link breaks, we assume we have detected the loss of the lines. So the costs are written in red. Now, C and B know that the line is broken. How can they know that the line is broken? Well, if there is a direct physical link somewhere, the physical layer will tell you the thing is broken. There will be a LED that doesn't work somewhere on the adapter. So it will sense that the circuit is open. If there is not a direct physical link, if there are switches or repeaters or some kind of things in the middle, then you typically will have a keep alive mechanism where nodes like C and B, if they run a routing protocol and they are neighbors, they send to each other every few seconds or every tens of milliseconds, they send a heartbeat message saying, I am still there, and B can reply, I am still there. So you can detect this. We'll see that in RIP, in distance vector, it is the similar mechanisms that I use. So they have detected it, and now the links are put to infinity. So we have the same algorithm as before, but now the values of the links are infinity. And the question is, what will happen? close in 5 seconds. The majority of you say B, the algorithm does not converge, and this is the correct answer. Let's see on a simulation here what would happen. So this is exactly the network. Now I have two parts of the network. In fact, the links between the left and the right are broken. We start from the initial conditions on the left. Then if we focus on C and E, what will happen? C will ask all of its neighbors, what's your value? So there's only one neighbor now, E. So we'll ask E, what's your value? The value is 3. Okay, my cost from C to E is 1, so I will get 4. So in the next round, we'll get 4, and similarly 5. In the following round, C will ask E, what was your value? It was 5, so now it will be 6. And E similarly will get a new value of 5. So we see that at every round, the values will increase here between C and E. Remember, those values are the distances from C to node 1, or from D to node 1. What is the true value of the distance? It's plus infinity. So in fact, the algorithm is, if you want, converging. It's not converging in the sense it's not stopping, but it is going to infinity, which is the correct value. So it's doing the right thing, but the right thing will take an infinite time. That's a problem, of course. But this is what the algorithm will do. So in some sense, the algorithm does the right thing. It's called count to infinity. There's like a ping pong between the nodes C and E, where each of them increase each other. Between parentheses, you can see that the rest of the network has worked correctly in this case too. So B and D have correctly computed the distances to destination. Well, here is the answer to the quiz of a few minutes ago. The answer is yes. If you start from arbitrary initial conditions, it will converge to the correct value, providing the network is fully connected. And if the network is not fully connected, it will converge to infinity it will go to infinity for those nodes that don't have a path to the destination. So in some sense, Bellman Ford is completely safe, at least in the sense of the semantic of what it's doing. It's not safe because if it counts to infinity, it means something bad will happen. If you run that in router, if you have a counter that grows forever, it will overflow someday. But from a mathematical viewpoint, the algorithm is doing the right thing. It is computing the correct distances to destination, regardless of the initial condition, which is quite striking. So this goes well beyond being the optimal algorithm or not. It's robust. If you do something wrong at one iteration of Bellman Ford, if for some reason a malicious node gives wrong values, and if it does it at only one round, for example, the algorithm will recover, will get back on feet, which is not the case for other shortest path routing algorithms. However, there is a catch. Now, if we start from arbitrary initial conditions, we have lost the physical interpretation. At round K, it is not true that the value we have computed is the cost of going there in at most K hops. So proving this statement is not based on just this intuition that we had before. Proving that Bellman Ford is correct with correct initial conditions is almost trivial. It's based on this interpretation that at round K, we are computing the shortest path in at most K hops. In the general case, it's a bit more complicated. The proof is in the next slide, but those of you who are interested can have a look, but we will not discuss it in detail. But that's a very important property. It means that Bellman Ford, whatever you do, if you do it rarely, will not impact the convergence. Rarely means if you do something wrong once, and then you leave the algorithm enough time to converge, then it will converge to the correct value. Which is, of course, vital to deploying this as a plug-and-play routing protocol. If something changes in the network, costs are set to infinity because a link is broken. A new router is added somewhere or a router is removed. So all of those operations change the topology, change the values of the graph, but there's no need to reset the algorithm. You just let it going on the fly. This is for centralized Bellman Ford. But of course, because it's easy to understand that now if we run it asynchronously, so we have shown a message passing interpretation where instead of saying, I have a global view of the network, at round k I compute all the values of pk, if instead of that I have a processor in every node of the graph, and the node, once in a while, asks from all the neighbors, what are your values? And then it does the computation we've seen before. When it's done the computation, it answers the nodes when they ask what is your value, or it sends to the neighbors what are the values. If we do this, we will have an asynchronous version of Bellman Ford where we don't have the concept of rounds. Some nodes can go faster, some can go slower. And it's not difficult to imagine because Bellman Ford is so robust, if some nodes are going faster or slower, it's like having arbitrary initial conditions. It doesn't matter, the algorithm will still converge. This is essentially what we will say. So what is the algorithm itself? Well, the algorithm itself, which I call prelim, distributed Bellman Ford prelim, because it's only a preliminary version. We'll see that we will need to optimize it to make it in the distance vector implementation. It does the following. It computes its best estimate of self to a given destination. From time to time, it sends its value to all neighbors. Therefore, from time to time, it will receive from neighbors its value. Whenever it receives an updated value from one neighbor or from a collection of neighbors, it does the following computation. It compares what it had before to what it would have if it would go through this neighbor. This is the asynchronous version of distributed Bellman Ford, and it's not difficult to imagine that it will do the job. Voilà, that's all we will see for today. So next week we will see how we can optimize this a bit and get what is really done in distance vector. So see you tomorrow for those of you who will be present.